Okay, so the topics that we will look at today is called a ground-based augmentation system. Okay, you may not need to for some of you like G, you may not need to pay attention to every single detail, but I think the understanding the idea is okay. But for Pure, it is important to understand the concept and algorithms because this is the reason why we have some projects with our Japanese partner, for example. Okay. So what we are looking at today is the topic called ground-based augmentation system, okay, or GBAS. So let me go and look at this slide, okay. So while when an airplane, which also utilize GNSS and traditionally GPS, to locate their position in order to have a approach and also landing. Okay, approach mean the airplane is reducing the altitudes and it is approaching the runway. Okay, so it approaching the runway. That's what approach mean. So landing means you're planning to land on the runway as well. Okay, and when we talk about precision approach and landing, it means we are approaching and land with some type of precision requirement that we have to satisfy. Okay. So because it's related to safety in general, when an aircraft is trying to approach, is approaching and for landing, there are different phases. Okay, we call phases of flights. Okay, but this is like toward like the last part of the flights. Okay, so these phases of flights include LNAV, VNAV. Okay, it includes LPV. Oh, sorry, one moment. Okay, sorry, there's some noise from outside. It come up occasionally. Okay, so while the plane is approaching, there are different phases or different levels of approaching and landing. Okay, so in general, we can talk about LPV or APV. You know, and these LPV actually it's down to they have like different categories like LPV1 and LPV2. Okay, and for LPV, the decision height is generally is called 350 decision height. Okay. What does the decision height means? It means it is the height from the ground. Say, let's say that this is the 350 feet. Okay. So when the plane is lowering the altitude to this level, it has to decide whether to go ahead with the certain requirement. Okay, so the pilots, when is it reducing the altitudes? Okay, so it has until 350 feet to make decision whether to use the mode on the screen called LPV. Okay. It can it if the system wants that you cannot use LPV, it means the system probably understand that we cannot satisfy this type of alert limit in the vertical and also in the horizontal. Okay. What do we mean by alert limit? I guess I have never talked about this before, but maybe I can go to on page 3 and then draw for you. Sorry, maybe I think in the picture, maybe it is somewhere. Oh, this is it. Yes. So in general, this is on page 41. Okay. So this is related to what is called alert limit or AL versus protection level or PL. Okay. Which has horizontal and vertical. So when an airplane is flying, okay, here, there are two types of values that the airplane has to be aware of. One is protection levels. Okay, protection level is like the estimated positioning error. Okay, of the airplane, which has both the horizontal, which is HPL, and also the VPL. Okay. And at different time, the aircraft can compute the protection levels differently because the errors of the position, they vary like randomly. Okay. In a way, protection level is quite similar to positioning errors, but it's not exactly the same. Okay. When you compute the positioning error, you know the reference position. So whatever you obtain from the system, you subtract and you get the error. But the airplane is moving very high speed, so I mean we cannot find the exact positioning error. So all the systems will compute what is called protection level. Okay. So in a way, you can think of protection level of an airplane similar to positioning error of an airplane, but it is not the exact positioning error. It is the estimated positioning error. Okay, and how to compute that, we will look in the lecture today. Okay, so at any altitude equals to x feet, an airplane has to monitor protection levels and also monitor alert limit. Okay. For the alert limit, it's like a bigger box. It's like a bigger box. It is a red box that also covers an airplane. The PL, which is the blue lines, it is more like the box of the errors of the aircraft position. But the big box, which is the red box called alert limit, is bigger. Generally, is bigger than PL because we want to make sure that it's safe. Okay. So this alert limit, it also has horizontal alert limit and vertical alert limit. Okay, and they depends on altitudes. Okay, meaning that in general, when the altitude is higher, the alert limit box can be bigger. If the altitudes of an airplane, not latitude, sorry, altitude is the height. Okay, altitude is the height of an airplane from the ground. Okay. So in general, when the airplane is very high in the air, like let's say it's in the en route is like about 30,000 feet from the ground, then this box is very big. It's like kilometers. Okay. But then when the airplane is lowering the altitude or the height lower and lower, this alert limit box will become smaller. Okay. So it means that for high altitude, this box is very big. Okay, for the alert limit. But then when it's at low altitude, the box becomes smaller. Okay. But the airplane, which the error of the positioning error of an airplane, generally it's just in here. Doesn't change so much, but it's random. Okay. This is like PL. Okay. So PL is like the estimated positioning error at any time, which is also random. It's like if you fix alert limit at one time, the blue box it will moves bigger and smaller inside the alert limit in general because the error is not fixed. Okay, it's random. And this is what we call alert limit and protection levels. Okay, you have any question on this slide? I'm gonna go back to page 2. Any question? So this is the very important concept. It is used in autonomous car. It is in drones. It is used in planes. Okay, it is used in all these moving devices that you want to control safety. Okay, and in general, what is called is when the plane is approaching at different altitude, right? The alert limit becomes smaller and smaller. So if the protection level is higher than alert limit, we need to give warnings to the aircraft that we cannot use that particular mode or particular function. Okay. If the protection level is below alert limit, then we can still always use the that mode. Okay. Anyway, so any question on this slide? And anyone? I know that Pio has listened to this before, right? But maybe G
Yes.
has never listened to this. So Pio is more like a review. Okay. And, G, do you have any question?
Now not.
No question. No question means you understand everything. That's very scary. Okay. I always tell you one one should have question when you learn something new every time.
I want to translate this slide again, teacher.
Well, you can watch the video before you come to lecture because we have a
Yes.
Thai version in YouTube.
Yes.
Okay. But you should ask a lot of questions always. That's
Yes.
important. So when the plane is reducing altitude, down like this, okay, it can use different modes like LNAV, VNAV, LPV, Cat 1, Cat 2, and Cat 3. Okay. And if you take a look, also for the LPV, uh, uh, for LPV, it means that we have the alert limit for vertical at 50 feet, alert limit for horizontal at 40 meter. I'm sorry, 40 meters. Okay. And decision height or DH. Okay, this is the height where the pilots can decide whether to use this mode or not. Okay, because if the pilot thinks that is not safe, or the pilot has received some warning from the system that it should not use, pilot can also land by using eyesight. It is also possible. Okay, or the pilots can decide to cancel the landing. Instead of landing, it goes up and then comes around again. An example. Okay, and so for the LPV this one, they can be divided into LPV1, LPV2. Okay. And sometimes in some system they talk about another. See, when you down to like 200 feet decision height, okay, here you can go ahead and use cat 1. Okay, cat 1, another name is APV 200. Okay, 200 represent 200 feet. Okay, so it around 200 feet from the ground. So what is 200 feet in meter, Pure, roughly?
Oh, 60 meter, 60, 65.
Yeah, it's about 6065 meter, right, from the ground. Okay, which is not high, right? It's not high for an airplane, right? 60 meter from the ground for the plane is not high. It has up to that level, that height, to decide whether to just go ahead and use Cat 1 or not. Okay. And for Cat 1, the alert limit, now we don't talk about horizontal limit so much. Now we talk about vertical limit because vertical is important for landing, right? You don't want to hit the runway. So vertical alert limit for Cat 1, it is set as 12 meters. Actually, in some case, it's the 15 meters. I see so many different numbers. But recently, they said that they increased this to in 2018 standard by ICAO. I think they increased to 35 meters for Cat 1. Okay, and then uh, and then for horizontal alert limit, I think it's still 40 meter fixed. Okay, and for Cat 1 can be divided into Cat 1, Cat 2, and Cat 3. Okay, Cat 1 is similar to the system called ILS system. I think we haven't talked about it, but next semester I'm teaching a course in aeronautical communication. You can join and then understand the first part of the lecture, which is about some navigation part without GNSS. Okay, and ILS is one of them. Uh, so you can think of ILS as analog system to help guide airplane to the landing. No, but Cat 1, Cat 2, Cat 3, they are more like the digital version. Okay. So for Cat 2 and 3, the decision height becomes smaller, like 100 feet. And for Cat 3, this is used for what is called auto landing. Okay, meaning that even if there are fogs or heavy rain, the system will land automatically. Okay. Nowadays, for Cat 1 or before Cat 1, the pilot still has to look and see the. So Cat 1 only is allowed until 200 feet from the ground. Below that, you need to look with the eyesight, which or sometimes it's called visual. The pilots have to use visual to land. Okay. So yeah, that's that. Let me go again. So these are the name, for different phases of flights related to approach and landing. Okay. For phases of flight related to airplanes, there are some other phases as well, like departure, en route, like the different part. But this is related to approaching the runway and also landing on the runway. Okay. So at the moment, all the standard uh, in the world, they are only up to Cat 2, not Cat 3, meaning that auto landing is still not possible. Okay. So in the past, there are two types of approaches for the airplane to approach the runway. One is ILS. This is the based on like a radio system. Okay. If you're interested, you can look at the I can send you the slide later, but basically, this is how the plane is guided to land on the runway, okay, by receiving radio signals. And if the airplane uh, is is not directly at the center of the runway, they will receive some tones of signals more than other tones, and that's how they know whether they are on the center or not. Okay. And for now, with additional approach based on GPS or GNSS, then we have like various type of uh, uh, phases like LPV, LNAV, VNAV, and and APV and so on, and also CAT category 1, 2, and 3. Okay. So on the rooftop of the 12th floor in engineering building, it is where we have experiment with the ENRI, which is a Japanese organization, and also with the Aerotai in order to work on this type of system. Okay. But we are not developing standard. The standard is developed by ICAO, but a lot of these data are discussed in ICAO at the regional office in Bangkok as well. Okay. So let me see. Uh, Actually, for this tool, I can. Uh, okay. So these two maybe I don't need to talk about. But here, if you talk about LPV, okay, LPV when for the airplane, when an airplane is approaching, let me change to red colors. When an airplane is approaching the the runway and then to land, okay. So when the aircraft, this is aircraft, it is approaching and landing. When it's approaching the runway, generally it will get it gets increasingly sensitive and becomes linear as you approach the uh, and becomes linear as you approach the threshold of the runway. Okay, it's like where you need to decide to land or not to land. Okay, but if we talk about a system like LNAV, VNAV in general, so they're not so sensitive and not so precise. So in general, wherever you are, you get similar performance. Okay, so it's linear, at the all level of the approaching. Okay. Uh, when you look at the chart, when as a pilot, when they look at the chart, okay, so they will have a various category of approaching that they can use, like LPV, LNAV, VNAV, and so on. Okay. And for each runway, they have to specify with something like this, so you know whether the airport support this type of phases or not. Okay. If the airport supports this type of landing, it will have this type of say RNAV and then GPS. Okay. You can for RNAV maybe you can put a question mark here first because we haven't talked much about it so far. Because basically this lecture is geared more toward like aviation, aeronautical navigation. So there are a lot of vocabularies related to aviation that comes up. Okay. So if I haven't talked so much about them, then of course we have more time later to go deep into it. Okay. So what is ground-based augmentation system means? Okay. If you will see this term come up quite often, augmentation, okay, it comes from the word augment, okay, which mean to helps or to aids, okay. So it is a system that helps users. Okay, so it's a system that helps user, for example, aircraft, to have to have to have like performance requirements. Okay, and what are the performance requirements? Okay, one is the accuracy. How accurate is the position? Okay. Two is the integrity. Integrity, it is a very special word. If I can go briefly about it, integrity is how much you can trust, these errors or this accuracy. Okay, so in a way, is a trust on the accuracy on the or the errors of the position. Okay, and then you need to be able to give warning if the accuracy of your position will not satisfy uh, the level specified in the standard. Okay, let's say that if you have to satisfy the position by the alert limit, right, and you have to control within 40 meters, if the aircraft will not be able to have that type of accuracy, the system has to warn. Okay, and that's what it means. Then number three is what is called continuity. Okay, continuity is related to how long you can have one and two. Okay, so it's like a continuous performance. Oops, sorry, my board is getting. So it's continuous operation with the performance of 1 and 2. Okay. And lastly, the fourth one, the performance is called availability. Availability. Okay. Which means we need to have 1, 2, and 3. If we have 1, 2, and 3, then we say the system is available. Okay. So in general, if we look at this type of performance, we can draw them like this. Inside, we have the accuracy, right? And then we have integrity. Integrity is to be able to have this accuracy and be able to have some warning. We have the trust on it. Continuity or C. Okay, continuity is when we have accuracy and integrity for extended amount of time. Okay, and if we have if we have all of these, then we call availability. Okay, so this is the four. So these are four. I don't know what something is wrong with my board again. You just draw a circle around it, basically. Okay. Let me try to use this part. Okay, so this is availability, AV. Okay, so for any system that requires safety, okay, we always need this type of approach, safety. Okay, this is different from typical positioning system where you don't have to guarantee all four. Okay, in your mobile phone, which of these four do you need to guarantee? G. On mobile phone, of these four performance, which one do you have to guarantee, you think?
Continuity.
Nope. How about G? On mobile phone, it's not about safety. Okay. G, are you there?
Yes.
Okay. So out of this performance, what do you think in mobile phone we have to satisfy out of these four?
Accuracy.
Yep. Only accuracy. Okay. So in the mobile phone, for positioning purpose, they only give accuracy, but they don't give integrity. They don't give continuity. They don't give availability. Okay. Only when you use positioning for safety purpose, like autonomous car, drone, because taxi drones maybe, but package drone, I don't think they have four. Okay, but if you use like a taxi drones, like a drones that is a taxi, autonomous taxi, yeah, you need four of them. If you use for airplanes, you need four. Okay. So these are the four. And let's take a look at what it means. I don't know if I think maybe one page there's something like that. There any page, let me see. That shows these parameters. No? Shit. Let me go to another page. Because for our system, you need this type of let me see, is it here? So I cannot find any slides today. I need to look for that. Or maybe it's in introduction. Maybe they have it here. One moment, okay? I'm trying to look for this slide that has all these parameters, but I haven't. Not sure I didn't find it earlier. Maybe it's this slides. Navigation performance. Let me share this slide to you as well. Yeah, this is the slide that I was planning to find earlier. It is about haven't used this much. How can I show this? Okay, I shared the file to you already. Okay. This is in Google Slide, right? How do I make presentation? Slide maybe? Oh. It's okay. Maybe we can look from here. Yeah, so this is the what I was trying to find earlier, but I couldn't find it. So when we talk about navigation performance, we have accuracy, we have integrity, continuity, and availability. Okay. For accuracy, I don't know, Google Slide, do they have like a button to make presentation or not? Has anyone used Google Slides? Yeah. Maybe it's in one of the menu. Present. Well, view, maybe it's a view. Present. Okay. I think this is it. Okay. Yeah. So this is what I was trying to show earlier. Okay. But I shared this slide to you already. No, you can take a look. When we talk about navigation performance, there are these 4 parameters. Okay. In your mobile phone, we only care about accuracy. But for any applications that require safety, then we need integrity, continuity, and availability. Okay. For example, if we talk about accuracy, okay, accuracy is like the navigation system error or positioning error. Anyway, uh, we can express in terms of, we normally use 95%. Okay, so if you put a histogram of, oops, I don't know if I can draw here. Oops. Nope. Mhm. So if you, maybe I can download this file instead and draw in the, so please download this file, no, that I share to you so we can take a look together. Okay, so let's take a look at first one, which is accuracy. Okay, so accuracy is very simple, right? It's just positional errors. You know, you have the XYZ computed minus XYZ true, right? That's errors. And you can have accuracy in horizontal accuracy and vertical accuracy. And normally we look at 95%. Okay. 95% mean if you plot like the horizontal accuracy, HPE, okay, you have some type of Gaussian distribution like that. Okay. So we cut at 95%. Okay. Here is 95%. Okay. And you learn from probability already. If we look at 95% or 2 sigma, okay, what is the probability? Is the, so the probability of having errors above 2 sigma, okay, is the probability of HPE, okay, larger than 2 sigma, okay, which is Q of the value of 2 sigma minus the here, which is typically 0, okay. divided by sigma, which is Q2. Okay. And I don't remember what is Q2. Q2 is probably 10 to the negative something. Okay. So we cannot say error, like for all errors, we always look at 95%. Or you can just draw the histogram and then you cut it at 95% of the total data. That's fine. And that is what is called in the standard 95%. Okay. So for this type of various operation or phases of flight, okay, for example, en route, like when you are 30,000 feet from the air, then the accuracy that you have to maintain is at 3.7 kilometers. For vertical, there's no requirement because it's too high anyway. Then if you look at APV1, the horizontal accuracy is 16 meter. Vertical accuracy is 20 meters, for example. And then for Cat1, then we look at the 16 meter as well. But both of these have changed to 35 meters in 2018 ICAO. Okay. And Cat1, the vertical should go down to like 36. This is category 2 and 3, I think, not 1. And well, next is integrity. What is integrity? Okay. Integrity is the ability for a system to provide warning in a timely fashion. Timely means fast enough, depending on where you are. Okay. So if the system has some problems or the system has some anomaly, then the system will warn the users. In this case, it's the aircraft. Okay. And for example, so for example, for the en route, they have this type of numbers like integrity is in every 1 hour, the integrity is 1 minus 10 to the negative 7. Okay. Of course, there's a chance that you cannot provide warning in time. Then that is called integrity risk. Okay. เหมือนแบบถ้าเตือนไม่ทันน่ะนั่นแหละ with very low probability 10 negative 7 over 1 hour, for example. And for en route, how fast you have to warn? You have to warn within 5 seconds. Okay. So this is like an example of what it means. Okay. Integrity is probably, you can put a big star on it. Integrity is it is very not difficult to understand, but some people seems to not understand it. Okay, that's what I'm saying. Okay, next is the I'm not gonna go deep into this. Next one is a continuity. Okay, so continuity is the it will look at the probability that the system can support accuracy, which is performance number 1, and can support the requirement for the integrity, which is the performance number 2, for a duration of intended operation. Okay. For example, if we are at en route, okay, the continuity can be at 1 1 minus 10 to negative 4 per hour up to 1 minus 10 negative 8 per hours. Okay. Which means that the risk of not having the continuity like this is 10 negative 8 per hour. Okay. And what does it mean when we say that we cannot detect it is a risk? So the risk to continuity is the probability that there's a detected but not not planned for navigation interruption after the start of the flight or the start of the operation. Okay. So in order to compute continuity, you need to satisfy performance 1 and 2. Okay. And lastly is availability. Okay. Availability is the percentage of time that the navigation system is usable or operational together with all the performance number one, number two, and number three. Okay. For example, so in a way, it is like a portion of time with the reliable information. Okay. For example, when they talk about en route, availability is set to 0.99 to 0.99999. Okay, for example. And uh, so this is next one. This is the picture that gives you the overall picture of performance requirements of the signals, okay, at different operation or different phases of flights. Okay, if you are en route, okay, horizontal accuracy is about 3.7 kilometers or 2 nautical miles. Okay, integrity is 1 minus 10 negative 7 per hours, which means this is integrity risk. Okay, time to alert is 5 minutes. And then continuity is the, like in the example, the availability is like this. Okay. And when we have the aircraft at low and lower altitude, when this arrow means low and lower altitude, let's say you are at um, say initial approach, meaning that we reduce the altitude trying to approach, but not so close to the airport yet. Maybe horizontal accuracy now is reduced to, instead of kilometers, now it's meters, like 200 meters. Integrity is often quite similar. So it's 10 negative 1 minus 10 negative 7 per hours. But now time to alert is, instead of 5 minutes, now it has to be 10 seconds. Okay. So if we cannot alert in time, the system has to warn users. Then continuity is still the same, I think. And then availability is the same. And if you go down to APV1 or APV1, for example, so it becomes horizontal accuracy has to be 16 meters, vertical accuracy is 20 meters, integrity and the time to alert is now fixed to 10 seconds. Continuity is like this. But now instead of every hours, then it's per any 15 seconds, because for landing purpose 15 seconds is very fast, already almost landing. So you can take a look at these as performance. And then if you look at cat 1, cat 2, and cat 3 that we are very interested. For cat 1, horizontal accuracy is about 16 meter, vertical accuracy 4 meters. Okay, integrity, time to alert now 6 seconds. Okay, and the rest is quite similar. Okay, if you go down to cat 3, which is auto landing, okay, meaning that the pilots can close their eyes and they just land, then the horizontal accuracy has to be 5 meters, vertical accuracy is 2.9 meters. Integrity now is very low, no? At this 2, 1 minus 10 negative 9 per approach. So very low probability of risk. Also, time to alert is 2 seconds now instead of 6 seconds. Okay. But for availability and all this, this is like flexible. That's why they list it like this. Okay. So that's all for this slide. Just like a very quick introduction about performance and what it means. Okay. You have any question about these slides? Then I go back to Jibas. Any question?
No, not for these slides.
Okay. Now then let me go back to Jibas and then talk to you about it. Okay. Oops. Okay, so if we look at the system for GBus, what what does it consist of? So in GBus infrastructure, basically you have three parts of the component. One is the ground facility. Okay. Two is a space segment, and three is the users or airborne or aircrafts. So in Jiba system, basically we have a users, which is aircraft. Okay, is it approaching the runway? This is runway. Okay, and because we know that positioning errors will exist in any system. Okay, so in the Jiba system, you can call this like a reference station. Okay, so they will install about three or four receiver, 3 to 4, near the runway or on the runway. They have to decide. Okay, then it will. So this receiver will receive signals from satellites, for example, GPS. At the same time, the aircraft also receives signals from GPS to determine its position, right? So it knows its position. Okay. But because the aircraft is traveling away from the airport, sometimes up to like 20 to 40 kilometers. Okay. Let's say 20 to 40 kilometers while it is approaching the runway. So the ground station or the ground facility, it will receive signals like pseudo-range, and so on, and others. And then it will process these GNSS signals, and it will broadcast correction information to the aircraft, the approaching aircraft. The good thing about this is that for the ground station, they can contact and they can broadcast to multiple users. So if there are more than one aircraft that is coming to near the airport, the system can broadcast to all users, immediately. Okay. And so, what are the information that the reference station or the ground facility? What do they transmit? So they transmit the differential correction, says for pseudo range. Okay, they detect some failure and alarm user. Maybe they detect failure of some satellites, and so on. And the correction information, they will be put into frames, data frames, and then sent via the wireless connection, generally with the VHF uh, frequency. Okay, it's a digital communication system. Okay, so uh, so this is another picture that shows that the reference stations, the geodetic grade receivers will be installed at the runway. Okay, and because the receiver will know their own fixed position, so they can find these errors, which is C minus low. Okay, and this is one of the information to be transmitted. Okay, but there's transmit many things. Okay. In addition, if the ionosphere is not uniform, meaning that the delay from the ionosphere here, let's say that it is equal to one value, while here is different. Okay. Then this different station, they can compute this delta IONO and then gives correction information or give some type of statistical values like the mean standard deviation to the aircraft as well. So the different things they can send, and all this information is called augmentation information. Okay. Uh, and the coverage area is generally is about 40 kilometers around the airport. Okay. So it's only for approach purpose and landing purpose. It's not used for, flying over oceans, something like that. It's different. Okay. And the reason they say ground based is because the receivers, they are on the ground. Okay. That is why it's called ground based. If you talk about satellite based augmentation system, it means the satellite is the one that transmit correction or augmentation information. Okay. And what else should I show? Oh, some of this I can skip. No need to show everything. Okay, so what is the benefit of GBus? The GBus can support Cat 1, Cat 2, and Cat 3 precision approach. Okay. If we talk about the old system, which is ILS, I think ILS can support Cat 1 and Cat 2. Okay. They are like the older technology based on radio transmission, radio signals. And they've been installed for so long. So they will exist always. So some benefits, another benefit of GBus is for instead of having the approach path like that, looks very geometric, right? Try to turn angles and then turn again and again to go to the runway. This is the runway. Okay. So for GBus, they can have like a green type approach, which is more curved, and it will reduce the gasoline usage. Okay. So for GBus, the curved precision approaches are possible. Okay. No need to just go in the red line and have a turn like that. No need to. Another advantage is that for GBus, you can only have one station with a few GNSS receivers for all the runways. Okay. Theoretically, there's no need to install the reference stations. These are the reference station here. No need to install at every runway. Okay. But compared to ILS system, you need one set for each side of runway. Okay. Because for ILS, what it is like this. If this is a runway, okay. So for ILS, they have to install ILS at both sides. Okay. Because it has to transmit radio signals depending on which direction the airplane is landing. Okay, on one runway, the airplane can land on both sides, so that's why they need like two sets and switch around depending on the wind, depending on the scheduling. Okay, but for GNSS like GBus, you only need like uh, one set only. Okay, so if you think about an airport with 4 runways, okay, like actually in some countries now they have 5 runways. Okay, in Suvarnabhumi Airport we only have 2 runways, but we are expanding it to 3 runways. Okay, so let's say a big city that has 4 runways, you need 8 ILS set. Okay, but then for GBus you only need 1 GNSS reference station. Okay, so that's like one main advantage. So a single GBus station can provide in addition, this single GBus station can provide multiple types of service to multiple users and to multiple runways. Okay, meaning that different runways, different planes, they can have different service. So it's much more flexible. Okay. Anyway, and because it only requires only one set of station, so sighting means like how to set location for GBus helps that the airport has more land, has more space on the airport or airport capacity. Okay, because ILS normally consists of like a many antenna. Okay, they're very long. Okay, and they have two sets. One is the long type, and the other one is the vertical type, like the high type. Okay, so so what are the function? What are the frames in the GBus data frames? So the message type, this is MT or message type. Okay, the different message types transmit from control station to aircraft. Okay, one is message type 1. This provides pseudo-range correction. Okay, so we don't provide the positioning error correction. We provide pseudo-range correction, and then the aircraft will compute by itself. Each aircraft compute on its own, right? Message type 2 will provide other data related to GBus. Okay. Message type 2 will provide final approach segment data. Okay. Message type 5, I think this one is related to the availability of satellite. Okay. And also there's some other information like integrity monitoring for even for GNSS satellites as well. Okay. So let's see for aircraft. Uh, uh, so for aircraft subsystem, okay, it receives signal from GNSS, receive broadcast the signal from the ground station, right? So the aircraft will receive signals, measure pseudo range of each satellite, okay, applies correction from the ground, and then compute the position, velocity, and time. Okay, and the aircraft will extract information like satellite correction, satellite integrity information, and so on. There are different types of data that the reference station send to the aircraft. Okay. Let me see. So, what are the errors that an aircraft has to correct? Okay. One is called tropospheric error, error from the troposphere. This one is called TC. Okay. And they can just compute depending on the elevation angle. Okay. Depending on the height or delta ledge, the height between aircraft and the GBus reference point in meters. Okay. H0 is the height of the troposphere. This one is transmitted in the GBus type 2 information. So for each satellite with different elevation angles, we can have different TC, different or different tropospheric error for correction. Okay, so that's one of them. Do all aircrafts, are all of them equipped with GBus receiver? No. For the older generations, helicopters or older smaller planes, they don't have GBus receivers. Okay, only the new types like 747, 787 Boeing or 737, they can install additional receiver. Airbus, like a bigger type. Okay, so GBus is not used for any airport. It's only used for big airport in general. Okay, what does that mean? It means that an airport has to still support different services. It has to support ILS. Then it can support GBus, for example. Okay. So for aircraft or aviation industry, the authority or the service, they cannot just change service quickly. They have to sort of provide service to all generations of airplanes. Okay. Okay. Next, an error model. So how does the airplane compute the uh, all these like positioning errors that has been corrected and so on? Okay. So sorry, I think on one slide I forget one equation here. Somewhere. Yes, I think this slide. Okay. Let me write down what I missed. Uh, so when we compute the uh, corrected pseudo range at the aircraft, okay, how does it compute? So it is PC. Okay. So it is PC, which is equal to this is the corrected pseudo range, and this is the equal to pseudo range from the aircraft that the aircraft received. This is for each satellite, okay, plus the pseudo range correction or PRC. This one is from GBus, no? This is pseudo range correction, okay, and then add with the range rate correction. The reason we have to add range rate correction is because the pseudo range correction or the pseudo range. So this is like a pseudo range error. Okay, it is not constant at all time. It has like sometimes it's very fast, sometimes it's very small, very slow. So we have to put this type of range rate correction at the at final resolution. Okay, let's say you get pseudo range correction every 5 minutes. Okay, so but in between 5 minutes, you need to use range rate correction to help. It's like how fast, how the acceleration of the errors. But for this range rate correction, it is like the slope. So you have to multiply with the amount of time between the time that you have and the time that the PRC is transmitted to you. Okay. And then we add what is called tropospheric correction or TC or topo correction. Okay. Generally, topo correction, is can be computed from the formula. So it's from here. Okay. Also in the topo correction, there are some other terms as well. There are some other parameters. One is one that I didn't talk about is this NR, which is refractivity index. Okay. This one also transmitted by GBus type 2. So the plane does not have to compute by itself. It can just use the information. Okay. So for this type of TC, if you plot it together with elevation angle, for example, or theta I, okay, and this is TC. So generally you have something like this, okay. As the elevation angle is decreased, okay, then you have lower and lower tropospheric errors. Okay. And so that's that. Okay, so next, this one is the put a star on this. Okay. Okay. So this is an error model that has to be computed at the aircraft. Okay. Each aircraft will compute by itself. Okay. So because the aircraft at some point it has to compute the positioning, right? So it needs to know all the measurements errors. Okay. And in GBus, what are all the measurement errors? Okay. So all the measurement errors is written in terms of sigma I square, okay, where I is the I satellite, okay. And this is because we think that all the errors is Gaussian, okay. So we use sigma I square for to represent the variance, okay. So in general, the total errors for each satellite, okay, for the ith satellite includes many sources, includes various errors. One is sigma PR ground, okay. This is like the ground of a facility order, okay. It and then added with sigma PR air. Let me put I as well, no? Subscript I plus the sigma turbo as well, and plus sigma iono I. Okay. So what is each source? Sigma PR ground is the ground facility errors. Okay, depending on the type of, depending on the grade. Okay, so for equipment purpose in aviation, they call gas A, B, C, and D. Okay, and so some part of the errors in here is not only related to the equipment, but it has something related to multipath as well. Okay, so there are two things related. So that's that. Sigma PR ground, is this the airborne error? Is determined from the receiver noise estimate and also multipath model at the receiver on the aircraft. Okay, so this first one, the error is on the ground, at the receiver on the ground. This one is the error perceived by the receiver in the aircraft. Okay, next one is the tropospheric error. This one is the ionospheric errors. Okay, and then yeah, I think that's it. Okay. So please put like a box around here. So this is what we are in the aircraft. It has to compute. Okay. Okay. So let's take a look at each one. For sigma PR ground. Okay. So this is a standard deviation of the pseudo-range error due to the ith ranging source. Ranging source is just a satellite. Okay. And we assume Gaussian or normal distribution. Okay. So this one in the aircraft, it just computes. Okay. Depending on the coefficients A0, A1, A2, and also the elevation angle, which is theta I. Okay, this is elevation angle. And M is the number of reference receivers, number of GNSS receiver at the ground. It can be two, it can be three, it can be four. Okay. And then next, for the airborne receivers, the airborne receiver consists of two parts. Okay. So it's the airborne receiver noise, or the word airborne, you can just say aircraft. It's similar, not the same, it's similar. Okay. And So this the sigma PR air consists of sigma noise of the receiver and also the multipath. Okay, multipath we can just compute from the formula as well. So this one should be theta n, theta I, no, not theta n. Next one is the this term. Okay, this is like the noise level in the receiver at the aircraft. So this one it depends on the grade in the equipment as well. For A and B, it depends on the parameter A0, A1. Okay, and this is just theta I. Okay, which is elevation angle. Okay. So if you take a look at picture here, so the equipment grade A is generally is noisier than grade B. Okay, for grade B, the sigma value is smaller. Okay, and that's it. You can at the aircraft just sum all this together. Okay, and okay, next. Okay, this also important. Let me put a big box to it. Okay. For the ionospheric error, okay, or sigma iono, it computed from this term, which is the mapping function. Okay, mapping function from like slant to vertical. Okay, maybe you've seen it already. Multiply with sigma. Oh, actually, this is from vertical to slant. Sorry. Okay, it's multiplied with the sigma vig. Okay, and then multiplied with the slant range plus 2 times tau and then the velocity in the air. Okay. So sigma iono needs to know the sigma vig or sigma vertical iono gradient. Okay. I don't know. I have the picture in here. Okay. Sigma vig is like this. In simple term, no? In simple term, if you have two location one, location two, this is one satellite. Okay, you measure the delay of iono delta iono 1, delta iono 2. Okay, uh, this delta iono is equal to this one minus this one. Is the difference between iono delay at two place, two location. Okay, sometimes it is called gradient. Okay, but this is like the difference of slant delay, right? So we can convert this to vertical, and it's called then it's called delta sigma vertical iono gradient. Okay, and this sigma comes from what? It comes from when you plot this the when you plot this the delta vig, not sigma, no, it's like this. It's up and down. Okay, then we just compute sigma. Okay, this is in simple term what it is. Okay, of course you don't use the exact value, but you do something else like overbounding and all that. Okay, but this is where it comes in. Okay, and this sigma vig has a unit. Is the difference or gradient between two location. Okay, so we call this as spatial gradient. Spatial comes from space. Spatial gradient. Okay, and it has a unit of millimeters per kilometers. Okay, so that's why we need to multiply with the slant range. We need to multiply with the distance between aircraft and the GPS reference point to get the exact gradient. Okay, But then because the airplane is moving, so we need to add additional distance due to this movement as well. Okay. So put a star here. This is like a super important. So if you listen to some presentation in the lab, like Nice, okay, what he was the P Nice, what he was this trying to find is this sigma v, okay. Because this is related to ionos delay at different location, at different slant range, okay. So if aircraft is very far away, sometimes the delay is very different from at the airport. During quiet time, it is okay, but we are concerned with the disturbed time, like during bubbles. What is sigma weak? Does it exceed? Is it more than the safe level of sigma weak in the system or not? Okay, so that's what we try to find out. Another one that Pinay sometimes he makes presentation about is computing this multipath, uh, the sigma of multipath in the PR ground here. Okay, so that's like the second thing that he's trying to find. Okay, and then what else should I talk about? Let me see. When people talk about converting from uh, slant TEC or slant delay to vertical delay, okay, there are different models. If we think about ionosphere, which is the red area, as only one layer or single layer, this is called as a single layer ionospheric model, okay. Then you can use this term or mapping function to convert from slant to vertical. Okay, but in some papers, in some works by Dr. Maruyama, recently he divided this ionosphere into called two layers. So that work is interesting, and you can find the delay through ionosphere by combining two parts. Okay, which is layer 1, sublayer 1, and sublayer 2. Then you just add together. Okay. Okay. Next, what are the type of GBus message? Like I mentioned before, these are the MT. Okay. We are concerned with MT1, MT2. Yeah, let's look at two of these. No, the rest are not so important so much. So MT1, so this is a block, okay, that so it has the measurement. The first part is the header here, 56 bits. So it tells you the time. It tells you the how many measurements from how many satellite. It tells you measurement type. Okay, it tells you this is called like orbit decorrelation parameters and the orbit CRC. I'll talk about this later, no? And then uh, how long can each satellite last, or how long can you use it? And then it is followed by all these the data from each satellite. Okay, so this is like 1,640 bits. Okay, up to 18 corresponding satellite. This is for GBus. Okay, for GPS. But in the GBus standard, they now talking about some other type of constellation like Beidou or Galileo and GLONASS and so on. Okay, so oops. Uh, so in here, for type 1, okay, for type 1, if you take a look in uh, in the block, what do you have? First, you have for each measurement block. First, you have a satellite ID, issue of data, PRC, RRC, and then sigma PR ground. Okay, and this is the range that is allowed by the system. Okay. So meaning that sigma PR ground can be between 0 to 5.08 meter, for example. Uh, pseudo-range correction can be up to plus minus 300 meters and so on. Okay. Ranging source ID is here, depending on the number. They can be GPS, GLONASS, S-bus, and spare. So these are for future constellation. And this is like a detailed table from ICAO. You can look later, but what is important here that I want to focus is this part PRC, RRC, and satellite ID and Sigma PR ground. Okay, and these are the available values and the resolution. Okay, the resolution depends on the number of bits allowed for each type of data. Okay, and what else? Maybe okay. Next, let me go to type 2. So type 2, it talks about some other information. The type 2 message consists of header, consists of message, and then CRC. And message type 2 is related to GBus reference point and GBus related data. Okay. What are these data that we are talking about? Yes. So we can take a look at this table. So first of all, it will broadcast how many reference GNSS receivers are there at the ground station. Uh, Local magnetic variation, sigma iono gradient. Okay, so sigma iono gradient is in type 2. No, it is not in type 1. Refractivity index for troposphere. These are all troposphere. Okay. Latitude and longitude of the GBus reference point, height. Okay. It also gives you the K values. Okay. To compute the protection levels as well. Okay. So these are the two main types of data that I think that we can talk about it. That I explain. Some other types we don't use so much. I can just skip because the you from this slide you can look at meaning of each type. Okay, what it means. And let me see what else. Okay. So that's that. And before I go into like how to compute this protection level for GBus, let me look at these quickly. Okay. So at KMITL, we are having experiment with computing the IONO delay gradient using three GPS monitoring stations. Okay, one at KMITL, one at Stanford, one is at Aerotai. Yeah, Aerotai actually has three receivers because they are planning to install GBus system, right? So first, let's focus at the STFD and KMITL. It is about 12 kilometers apart, okay? Because we don't have an airplane for experiment, so it is generally acceptable to measure the gradients using fixed receiver, okay? So the delay or slant TEC from STFD, let's say this is one satellite. There are many satellites, no? This is one STEC at KMITL, okay? And when there are gradients, meaning that the ionosphere may not look uniform, okay? Then we are very important. We're not uniform. In general, you don't get same delay. You don't get same slant TC anyway. There will be some slight differences, no? Even during quiet time. Okay. So what we do is we compute the delay gradient or the STEC as equal to STEC of we have to make adjustment of this STEC at STFD, we need to add the receiver bias and satellite bias. Okay. For ChemATL, it's the same as well. We have the STEC that we compute from the Rhinex file. Then we add the receiver bias at ChemATL, and then we add the satellite bias. Okay. So the gradient is computed from the STEC adjusted STFD. So if we look at two specific stations, no, and then minus STEC, STF adjusted KMIT, okay. So when they are subtracted together, you notice that some term will disappear because we are looking at one specific satellite, so BS are the same here. So we will have what we have remain is STEC STFD minus STEC KMIT, okay, and plus the difference between receiver bias at Stanford minus receiver bias at KMIT, okay. Of course, maybe with some noises and so on, okay. So this part is called offset of the receiver bias. Okay. So this is like a standard way on computing the STEC. Okay. And once you plot this the STEC, whatever you have, okay, at different time, okay, then you compute this the sigma STEC, and then you convert to sigma vertical or sigma VIG. Okay. So in our lab, there are a few methods that we can use to compute the gradients or this differential TEC. One is this is the very direct method. Sometimes it's called LTIAM or long-term ionospheric something. It's devised by Stanford University. Okay, and it is the uh, because it's computing STEC, right? So it is based on two frequency. Okay. But in our lab, we work with Henry and Dr. Saito. We use the one frequency approach. Okay. For the one frequency approach, maybe I talk more deeply with Pure separately. Okay. For that part, because for the LTIAM method here, we use two frequency, which is actually fine because all the reference receiver we have two frequencies anyway. But there's some issues related to here, which is at um, uh, the offset of the receiver bias. Okay, so we have to find this and so what do we do? Normally we say that during quiet time, we will try to so in order to determine this offset receiver bias, so one approach is we estimate that we assume that okay during quiet time, like super quiet time, okay, this term, the difference between gradients from one satellite is zero. Okay. So what it remains is the difference between receiver bias. Okay. So this is like a bias. Okay. Whatever this value we call bias star, we just subtract this from whatever we receive in general for the STEC. Okay. So we just do the STEC star equals to the STEC minus this bias star. Okay, so for the two frequency, this is one simple way of doing it. And once you get this the STEC star, okay, then you can find this sigma VT STEC sigma VIC. Okay. So yeah, basically. Okay, and so these are the short we call short baseline experiments. So it's not far apart, 12 kilometers, 4 kilometers. Okay, and that's how we have experiment with at KMITL, Aerothai, and Enri. Okay, and now in the new phase, we also have NEC in from Japan, and also we have CAAT, which is the regulator in Thailand on the aviation. Okay, so now we have more colleagues. So also in the early part of the experiment for 4 years, we only analyzed GPS. Okay, but in the second phase, so phase one, so phase one, we we measure sigma v, okay, during quiet and disturbed time. Okay, and we are the first country in ASEAN that look at this experiment. Okay, and then we also look at GPS only. Okay, however, now we are in phase two. So for phase two, what we have is we don't just have GPS, we have GNSS. Okay, we still compute sigma v, but we also add another thing called the monitoring of the disturbance, or IFM. This one will be installed in December. Okay. IFM is to monitor iono disturbance. Okay. We can use AI to help. We can do many things with it. Okay. So this is phase two, and it will be installed this December. Okay. And so let's say we look at two stations like STFD and KMIT. What do we have? STFD, this is KMIT. Okay. So the signals, you've been to the station already, right? The signals just now we change to the new generation. It used to be ProPack V3. Now is the um, ProPack 6. Yeah. Now it's ProPack 6 at both station. Uh-huh. But Saito-san also installed Septentrio as well, because Septentrio gives us the scintillation as well. Okay, and the data comes to our lab at our lab room 3113, and then we do analysis and so on. So for example, if you compute the DSTEC in millimeter per second like that, so this graph is the differential gradient of 1 day. Okay, so we have all these signals. Each color represent different satellite. Okay, then what we can do is we can compute the PDF or histogram, no, which is the blue colors. Okay, and then what we can do is we can put a Gaussian distribution curve, a normal distribution. In this case, sigma is 5 point something. Let me see. 5.1. Okay. 5.1. And yeah. Anyway, so normally this sigma is in the range of this type of values, or less than 10 millimeters per kilometers for quiet time. Okay. So if you are away, if the airplane is away from airport by 1 kilometers, okay, the difference in the pseudo range is just 10 millimeter or 1 centimeters. Okay, if it's away from 10 kilometers, then you have a 10 centimeters difference in the pseudo range. Okay, so sigma weak like this is not dangerous or anything. But then for sometimes for disturbed time, we find that the delta gradient is all the way up here, like hundreds or almost 200 millimeter per kilometers. Okay, let's say it's about 200, no, 200 millimeters per kilometers. Okay, so if the distance is 1 kilometers from airport, then we have 20 centimeters. Okay, if it is 100, and if it's 10 kilometers between aircraft and airport, then we have 2 meters difference in pseudo range. Okay. In some countries, like in Brazil, they find the gradient all the way to like 500 or even 800 millimeters per kilometers. Okay. So for 10 kilometers away, then it is equal to 50 0.5 meters times 10, which is 5 meters difference. Okay. And this is what we try to find. Okay. This one is a repeat from previous page. Let's go away. Okay. This page, I talked about it already, right? Okay. Okay. So now how do we find protection levels? Okay. So I have no space here, but protection level is computed. Like, can I erase some of these pictures here so that we can? Oops, I cannot. Oops, my God. Okay. Do I have more space? No. Okay. So VPL, for example, is computed from the coefficient K. Okay, there are two types of K, KFFMD and KMD. Let me first use KFFMD times sigma vertical. Okay, sigma vertical comes from this one. It comes from sigma I. Let me put. No. It comes from sigma I that has to go through some operation. Okay. You look at this on the next page. So this the VPL is computed from sigma vertical. Please look at the next page. Multiply with coefficients. Okay. So basically, this sigma vertical for the vertical direction. This is like the error in the vertical direction. Okay. It's a Gaussian. Okay. So this K, when we multiply, it's basically it is like how many of sigma value. Okay, this is sigma value. So KFD will determine the probability of errors. Okay, so depending on how many base station are there at the reference station, if you have 1, 2, 3, 4, this K will change. Okay, and these K values will help determine the probability of errors of 10 negative 7, roughly. Okay. Meaning that if we compute this protection level, we have the chance of incorrect just 10 negative 7. Okay. So out of we have the accuracy of VPL, this value of 1 minus 10 negative 7. So very high probability. Okay. And if the number of base station on the ground we have more and more, like 2, 3, and 4, we can use lower and lower K. Okay, because this Gaussian will reduce in size. Okay, and the difference between these two K, this case FFMD comes from the word fault free misdetection. Okay, and So KFFMD is used when we assume that no reference station fails. Okay. So for KFFMDs mean no reference station fails. Okay. Because if you have like a number of reference station, maybe some fails, you know. So this is how they determine various like safety levels. For KMD, I think it is computed when they assume that one reference station fails. Okay. And that's why for m equals to 1, we don't use. Okay. So meaning that it's safer, it's more risky for KMD. But in general, let's just use KFFMD. You know? So now, how does sigma vertical compute it? Okay. So on the previous page here, this page, we have total error called sigma here on page 16. Okay, this is total errors. This is like total errors that comes from various errors. Okay, but this is the error in pseudo-range domain. Okay, so we will convert this error into vertical horizontal domain. And to do that, we just use similar transformation metrics like in positioning computation here. We use what is called projection metrics. Okay, so this is called the projection metrics or S metrics. When we just multiply this G metrics, which is the satellite user satellite geometry metrics. For each satellite, if you have n satellite, you put n lines. Okay, and so theta is the elevation angle. Z is the azimuth. Okay, and W is the sigma of the pseudo-range error due to each satellite. Okay, if there's no such, and normally this sigma just comes from this the sigma I from the previous page, from page 16. Okay, so this thing is just a transformation from how do you call it, from pseudo-range domain. Okay, so this P is in pseudo-range domain. Okay, to so this is like a corrected pseudo-range and convert it to the XYZ domain or ECEF. Okay, ECEF domain. Okay, and then we can compute vertical, horizontal, etc. Okay, so we use the same concept from positioning estimation. Okay, and this is quite similar to S-bus, you know, or other type of augmentation system as well. Just the errors come from different part in the system. Okay. And this metric S is called the projection matrix, which projects from pseudo-range domain into the XYZ domain. Okay. Once you compute this S, you will have X, Y, Z vertical, and then the S, and then the bias. Okay. And then for the lateral or horizontal, we can just use the values in the Y domain. Okay. For the vertical, this is the vertical near the runway, at the runway. We have to do a little bit of transformation. We use the vertical part for each satellite, no? I is the satellite number. We use the vertical component and the x component. And for x component, we multiply with the tangent of the glide path angle, which is about 3 degrees. Okay. Because if this is the runway, okay, the airplanes will come down with the angle of the GPA of about 3 to 6 degrees, depending on the geography. Okay. And then, so this S is just like the weights. In a way, they are the weights. Okay. So sigma vertical is computed from the uh, the weights multiplied by the total errors for each satellite, sum together and square root. For lateral or horizontal, the error sigma value is the total errors for each satellite weighted and then sum and then square root. Okay. So this sigma vertical can be used to compute VPL. This sigma lateral can be computed from HPL. Okay. What time is it? My God, I haven't looked at the time. Is it almost noon already? Shit. Okay. And so this picture is just the picture that I mentioned earlier related to the protection level and alert limit. Okay. So here we compute VPL, HPL, okay, at each time. Okay. But for alert limit, this one, we also have vertical alert limit and horizontal alert limit, okay, which depends on height of the aircraft from the ground or altitudes. Okay. And yeah, I still have one more slide. I'll talk about this maybe next time because I think today already a lot of information. Maybe we can, because now it's very close to the final exam, you know. I think maybe we can continue this lecture. Let me take a look. Let me first stop the recording first. I'm supposed to look at the MATLAB with you actually today, but no time. It will be too long. So let me stop the recording first and then talk to you, no? Okay, so let's do it this way. PO and G.
Yes.
Yeah, I think the lecture is quite long already today and it has a lot of information for you, no?
Yes.
So please go and review and maybe let's meet again one more time this week because we are a little bit behind.
Yes.
Let me see. And so on Friday, are you free on Friday? Uh,
Yes.
uh, let's say 10 a.m.
Yes.
Yeah, let's meet again on Friday at 10 a.m. And what I want you to do is uh, one moment, lectures on GNSS. So on Friday, let's meet for 2 hours. What I want to do is I think you still have some short presentation on your work related to analyzing Android data, right?
Yes.
Yo, so that part. And secondly, G and PO, I want you to have a short summary of this lecture, maybe half and half. You can divide yourself, no?
Okay.
About maybe 10 minutes each. So I understand that you know what we talk about, okay?
Yes.
And
Now,
then
lectures on GPS.
second,
Today lecture on
second.
a review for the today lecture on GPS.
Yeah, I think it's a good idea. Yeah. Just the main point, what you have, what you learn from today's lecture, okay? And then I will give a short lecture on the Stanford charts, how to derive the Stanford charts, okay? And not so long, but yeah, but it's very detailed. It needs a lot of logic, so maybe it's already too much information today. And then we look at the lab, the GBus lab, okay, because we have the laboratory already, right? So I
Yes.
think on Friday let's do 2 hours on this, and that we can finish it. No?
Friday 10 a.m.
Okay?
Yes. Friday 10 a.m. Right?
Yeah, 10 a.m. Okay?
Thank you.
10 to 12, no? So we look at whatever remains and we look at, and then we do lab as well.
Yes.
Because we haven't done the lab, but I want you to take a look. Because in the lab, we will basically run the whole system and use some example data and then compute the VPL, HPL, and then find this availability and all that. Okay. So it should be good. Okay.
Okay.
Yeah. Sorry, I cannot finish today, but maybe enough time, no?
Yes.
Okay. Okay. Any question before I leave? I'll go to office tomorrow morning,
Okay.
so we can meet still. No. Any question, G? One question. One question.
Uh,
Yes. In Thai is okay. Then I translate. It's fine, no problem. But English is better.
I want to that the size of an airport or runway affect the calculation or error.
No.
No.
But the only important part is the for uh, each airport generally on the ground is filled with many things. Yeah, very important issue is not related to technology, but is related to how to install reference stations. Where's the best place to install? Okay, if we have a very flat and barren runways, barren means ไม่มีอะไรเลยอะโล่งๆเนี่ย it's easy, not difficult. But because the runway and the airport ground, it has a lot of construction, small building, obstruction here and there. So it's very difficult issue actually. And let me show you one. Let me do on the whiteboard. This is one issue that maybe you heard P Nice talk sometimes. Okay, about the issue that we run into, and this is what it is. I don't know. Can you see the whiteboard?
Yes.
You can see. Okay. Now I'll write in there. Okay. So this is an issue that now we are running into at the moment. Actually, now when I talk about this, I can talk about two things. I really like talking about this thing. No, brush, highlighter, marker, pen. Okay. Number one is the we call sighting, or where to place reference station. Sighting comes from the word sites, which is locations, where to place reference station. Okay. So when you have a runway like this, if I look from the top view, okay, so this is a runway, right? On this side, we have ILS. Here we have ILS, okay. Around here, we have another system called VOR. And there are also some other construction here and there. so so sometimes it's quite difficult where to put the reference station. Yeah. Should we put here? Should we put here? Or if this is the second runway, you know, should we put here? This is the always issue. Yeah. Okay. And then another issue is if you look from side view, okay. If I look from the side view, this is ground. Okay. And if I put a reference station here somewhere, you know, but then it has to receive satellite from many direction. right? There are many satellites to receive signals from. Okay. So generally, it will receive satellite like these, like these, like these, right? But then, suddenly, because we placed the receiver on the ground, sometimes the plane they moves and cut off this signal. So it's like a so sometimes we find that at certain time the Rhinex data is distorted very short time, but it's like it's many cycle slip like then what do we do? Like yeah, I don't know. This is one problem we find always. Yeah. Anyway, this is aircraft, no landing aircraft. Okay. And next thing is about IFM, which is we call ionospheric front monitor. Okay. So this is like ground, right? This is reference station. We know that the ionosphere is up here. Okay. And then if there's some disturbance coming, we need to set up a system here and can detect this disturbance or large gradient. This is called large gradient. Yeah. So this is IFM. Yeah. We can talk about it next time actually. And we have to set it before runway. If this is runway, we need to know it before. That's why we set it most likely on top of the engineering building at KMITL. Because the plane, this is KMITL, right? This is the engineering building, the rooftop, right? And the plane comes this way, right? For landing. So we can detect some IFM here, and it is about, I don't know, 4 kilometers from runway. Okay. Yeah, this is the next issue we were trying to to analyze and trying to determine very fun. And this will be the first IFM maybe in ASEAN as well. That we will have equipment and some data for analysis very soon. Okay. Okay. I think I keep going on, and maybe I don't finish. So you can copy this. I don't know. I just draw it for fun. Okay. Okay. Any question, Pure?
Yes,
I
about the
yes.
one, as you say, one, we assume the difference between the receiver bias based on the quiet state, right?
That's one approach. Yeah.
Yeah.
That's one approach. Yes.
That's the approach using LTIM.
Yes.
Oh, yes.
Yes. Because the thing is, if it's biased, then it doesn't affect the sigma, right? Sigma is about fluctuation,
Yes.
right? So if the fluctuation of the gradient is much faster than the bias, they don't fluctuate like that, right? They just
Yes.
slowly.
Slowly.
So it doesn't affect the sigma too much. So we're not talking about the levels, we're talking about the sigma. So, like when you think about it, okay, now I have something more to talk to you. Um, when okay, just for simplicity, let's look at this case. We have signals, okay. Let's say we have signal like this. I just draw for fun, no? Okay. So this is signal, let's call x1. We can, let's say it's random, so we can find sigma 1, right? And during this time, if the bias, we have bias that we have to move this thing down with this bias value, okay? So it will become like this. You know what I mean? It looks the same, but it just changed the level. What do you think about this sigma? Let's call this x2. How is this sigma? Is it different from sigma 1?
No, it's not that different.
Exactly, it's the same, right? Because for this thing, if you plot histogram or PDF, you have this thing. Let's say the mean is at M1, right? But then when you convert to the green, the blue colors here, it looks the same. It's just the mean now maybe at M2. Actually, we want it to be at 0. Yeah, but sigma is the same, you know. Sigma doesn't change. So you know the concept, right? Mhm.
Yeah.
Yeah. But then you may ask, then what's the point of trying to find the sigma weak from single frequency? Okay. So I think one of it is that we think that on the airplane, the receiver, only can receive just single frequency. So it mimics better, you know. Yeah, you know what I mean?
Yes, I see.
Yeah, but on the ground, of course, you have two frequency, three frequency receiver. That's fine. But on the plane, it's single frequency. Yeah, so that's one issue. That's why we try to find gradient from different point of views. Yeah. In Have you heard of the method called time step?
One step,
Yeah.
not yet.
Time step iono gradient. Okay. The one that Saito-san used is called uh,
SFCB,
station pair, right? They call it single frequency.
yeah, SFCBCA.
Yeah, for that one, it's the same. You have a KMATL, you have a STFD. Same thing, right? Not change, but it's just instead of using two frequency, they compute from one frequency only. Yeah. Okay. And at the end, they want to find the delta single difference. Single difference is the difference between line 1 and line 2. Okay. The single difference. And they try to find this sigma weak as well. Yes. So in here they use the common filters. Okay. I can go into through details after we talk about common filters in matrix analysis course. Okay. Then maybe you understand like picture better in details. So this is the second method, right? And then we have the third method called time step. Okay. So time step is used for also to find sigma weak as well, but it's used for an area where you don't have many receiver, you have one. Okay. And so what they do is the name tells is a time step, right? Okay. So during two times, T1 and T2, okay, we have a delay from iono delay that we can receive. Okay. If T1 and T2 is very close, meaning that delta is small, okay. These two line 1 and line 2 should be quite similar, right? Because then just close small time difference, not so much, okay. So this is called time step. Delta SD time step is called delta 1 minus delta 2. Okay. So in some work like from Brazil, they look at time step because they have like in their work they have like one single receiver but large area, and then you don't have two stations, so they look at the time step. But time step also has some other issues as well. Yeah, but let's not get into that yet. You can ask P Nice about it because he
Okay.
published one journal paper on this. There are some other bias that comes up basically. Yeah. Okay.
Okay. Thank you.
Yes. Okay. So let's talk to you again on Friday, right? Okay.
Yes.
Okay. See you on Friday. Mhm.
Thank you.
Thank you, teacher.
Yeah,
Thank
yeah,
you.
yeah. No problem. Okay. Keep asking. Good, G. Keep doing it every week, no? Maybe next time, two questions, three questions every time. So you like very expert in questioning. Okay.
Okay, teacher. Thank you.
Thank you.
Okay. Okay. Have a good day, everyone.
Yes, you.